Have you ever stopped to think about how the internet actually works? I mean, it feels so smooth and seamless, right? But underneath that calm surface, it's a total whirlwind of digital chaos. In this explainer, we're going to pull back the curtain and see exactly how our data gets from point A to point B perfectly intact, and we'll do it by looking at two crucial protocols that make it all possible: UDP and TCP.
Seriously, think about it. You're streaming a movie. You're in the middle of an intense online game. You're sending an email. It all just works. But the messy reality is that the internet is constantly dropping, duplicating, and scrambling your data behind the scenes. The experience you have, it's a carefully constructed illusion of order. And today we're going to see exactly how that illusion is built.
So you hit send on a huge file to a friend at, say, the University of Oceania, and just moments later, they have it. Not a single byte is missing. How in the world does a piece of data navigate a global network that is, at its core, completely unreliable and still arrive in one piece? That's the big question we're tackling today.
Okay, so at the very bottom of all this is something called the Internet Protocol, or IP. And you can think of IP as a really, really basic courier service. It chops your data into these little packages called packets and just sends them out into the world. But here's the catch. It makes zero guarantees. Packets can get totally lost, they can take different routes and show up out of order, the data inside can get scrambled, or they might even be sent twice by accident. It's a total mess.
Right. So to deal with this pretty careless courier, we build another layer right on top of it. And this layer is all about choice. You can think of it as choosing between two highly specialized shipping companies. Each one has a totally different philosophy for how to handle those messy packets, and which one you choose depends entirely on what you're sending.
First up, let's meet the speed demon of the duo, User Datagram Protocol, or UDP. If you need something to get there fast, and I mean right now, and you can live with a little imperfection here and there, UDP is your go-to. It's the courier that just grabs the package and runs, no questions asked.
See, UDP's whole reason for being is to cut down on delay. Think about playing a fast-paced game on a platform like Quantum Leap. You care way more about your actions registering instantly than you do about a single, tiny pixel being out of place for a split second. UDP prioritizes that real-time feeling by not wasting any time on fancy error correction.
And what's really cool is you can see why it's so fast just by looking at this. This diagram shows a UDP segment. Its header, the administrative part of the packet, has only 4 fields: where it's from, where it's going, how long it is, and a checksum. That's it. Less paperwork means faster processing at every single stop along the way.
Now, UDP isn't completely reckless. It does have one little trick up its sleeve for reliability: the checksum. But here's the crucial thing to understand. A checksum is like a quality control sticker. It can tell you if the package was damaged in transit, but it has no power to magically repair that damage.
So how does this actually work? Well, it's basically just math. The sender takes the data, let's use the word OLA, converts it all to binary code, and then performs a specific mathematical operation on it to generate a unique number. That's the checksum. That number gets attached to the data. When the receiver gets the packet, it runs the exact same calculation. If its number matches the one that was sent, fantastic. If not, the packet is corrupt and it just gets thrown away. Simple as that.
And this slide, wow, it shows you exactly how this works. Let's say during its journey, our OLA packet gets a single bit of data flipped by some interference, and it turns into MOLA. Just look at that. The resulting checksum is completely different. The receiving computer sees the mismatch, knows the data is bad, and just discards it. No attempt to fix it, just drop it and move on. That is the UDP way.
All right, now let's talk about our other shipping company, TCP, the Transmission Control Protocol. If UDP is the fast, no-frills courier, TCP is the high-security, registered mail service with delivery confirmation. It makes an absolute guarantee that your data will arrive and that it will arrive perfectly.
I mean, just look at the difference here. On the left, you've got UDP's simple 4-field header. On the right, that's TCP's header. It is packed with all these extra fields for things like sequence numbers, acknowledgements, connection flags, and all of that extra information is what powers TCP's incredible reliability.
So you're probably wondering, how does TCP actually pull this off? Well, it's not magic. It's a very meticulous, multi-step process that's designed from the ground up for perfection. First things first, before a single byte of your actual file is sent, the two computers perform what's called a three-way handshake. It's basically a formal introduction. a quick hello to make sure both sides are present, accounted for, and ready to communicate. It's really just a simple, polite conversation. Computer A sends a little SYN packet, which is like saying, "Hi, I'd like to start a connection." Computer B replies with an ACK-SYN, which means, "Great, I hear you and I'd like to connect back." And finally, Computer A sends one last ACK to confirm, "Excellent, the line is open." Only after all that does the real data start to flow. Once that connection is open, TCP's incredible tracking system kicks in. Every single packet gets its own unique sequence number. Think of it like a tracking ID on a package. And for every packet the receiver gets, it sends back a little confirmation message, an acknowledgement, or ACK, to confirm it arrived safely. It's this constant back and forth, making sure nothing gets left behind.
So what happens when things inevitably go wrong, like we see in this diagram? Let's say the sender sends out packets numbered 1, 2, and 3. But packet number 3 arrives before packet number 2. Well, the receiver immediately knows something is up. It was expecting packet 2, but it got 3 instead. Houston, we have a missing packet.
And here's the beautiful part. The receiving computer doesn't panic. It just holds on to packet number 3 and patiently waits. When the missing packet number 2 finally arrives, whether it was just slow or had to be sent again, TCP uses those sequence numbers to put everything back in the correct order, like solving a little puzzle. This is how you get a perfect file every single time. So we've got UDP for speed and TCP for reliability. Which one is better? Well, the answer is neither. It's never about which one is better. It's always about choosing the right tool for the job. It's that classic engineering trade-off.
This table really lays it all out, side by side. You can see it clearly. UDP is connectionless, it's fast, but it's unreliable. TCP, on the other hand, is connection-oriented, super reliable, guarantees order, but all that extra work makes it a bit slower. They are fundamentally different approaches to the same problem.
So why does any of this matter to you? Well, when you're watching a live event on ViewStream or making a voice call on ConnectSphere, that's UDP in action. A dropped video frame or a millisecond of garbled audio is way better than a long buffering pause. But when you're downloading your thesis from the Edgesphere University archive or just browsing a website, that's got to be TCP. You need every single byte to be perfect, period. And that leaves us with a pretty fascinating question to chew on. We live in a world that demands instant feedback, live streams, real-time collaboration, the metaverse. And that demand pushes us more and more towards speed. But our reliance on perfect data for things like science and finance pushes us towards absolute reliability. The internet of the future is going to be defined by how we continue to navigate this fundamental trade-off. So what do you think? Which one wins out in the end?